Welcome to Lecture 17A, entitled Line Integrals of Vector Dot Products, Definitions and Interpretation. The material for this particular lecture comes from Reading Assignment 4. That's the Introduction to Reading Assignment 4 and sections 1.2, 1.3, and 1.4. The objectives here are to basically give you some ideas to how to graph vector fields. Specifically, we'll stick with 2D because it's easier to plot. 3D just becomes messy, but in principle could be done. And the importance of geometry in developing an intuition, introduction to new definitions, and basically integrations of contour integrals, basically integrating around some form of curve, be it open or closed. So the specific concepts and visualization skills are itemized here. Basically, how to graph a vector field. Secondly, what is a vector tangent to a contour in 2D and 3D? A vector normal to a contour in 2D, a vector normal to a surface in 3D, the definition of a differential length vector, ds, s basically being lowercase, and the definition of a differential area vector, ds, in this case s being uppercase, definition of a scalar density, definition of a flux and a flux density. Flux density will basically be a vector, whereas a scalar density will basically be a scalar. The definition of circulation and circulation density. Circulation density will also have a vector format. And then definitions of averages. Note, this lecture introduces you now to new material, and it's quite dense, so it is advised that you read the relevant parts of the extracted notes in parallel. All right, so this is just a quick summary of the outline. First thing we'll be dealing with is the organization of this lecture in relationship to Reading Assignment 4 and also the lectures going forward. Second, that's the way forward until reading week, what we'll be doing. Third will be graphing in two vector fields. And then items 4, 5, 6, 7, and 8, basically just sort of a continuation in terms of what will be covered in this lecture. All right, so let's look at the organization of this lecture in relationship to Reading Assignment 4's material. Now, we'll be extracting basically the relevant information from the set of notes, and these are lectures 21 to 24. Between now and reading week, we won't be basically going to 24. We'll go only insofar as lecture 22. But in assignment 4, basically on the expanded version, you have basically 6 individual PDF documents, the main one being Introduction to the Divergence Theorem and Stokes Theorem. And then there are 4 individual appendices. Again, these are things that you do not need to look at, these expanded set of notes. And finally, there are solutions to Reading Assignment 4. So within Assignment 4, there are a number of problems, and basically all the solutions appear in a single document. This information also will appear as part of lectures 21, 24 in a separate area, but nevertheless, you have access to the solutions to the problem set assignments. All right, so let's look at where we're going between now and reading week. So I put here on the left side any videos or reading assignments for reference. In this case, the videos are available. You can look at. This is basically just going to be Reading Assignment 4, the shorter version that we're making reference to. And on this side, basically specifics of the Reading Assignment 4, and of course the extracted lecture notes, which are the only things that you're actually responsible for. And so, for instance, here, if you look at sections 1.1 through 1.5, this more or less is basically the contents of lecture 17 to 18, which are the extracted set of notes that you need to go through. Section 1.6 for Reading Assignment 4 is broken up into 2 separate lectures. So the lectures 19, 20 are the ones that you'll be needing to look at. Sections 1.8, 2.2, 3, 4, 2.7, are basically lecture 21. And then Reading Assignment 4, Introduction to Section 4, Part 4, and Section 4.5 basic constitute Lecture 22. And this is basically taking us up until reading week.
All right, so let's consider, for instance, graphing of vector fields. Well, we specify 2D because it's easier to visualize. If you try to graph a 3D vector field, you'll end up with vector fields crossing all over the place. It's very difficult to look at. So we'll just basically say that this material you can look into in section 1.2 of Reading Assignment 4. So let's consider this example of a 2D vector field. So f here is given by minus yx, and the question is, how do we interpret this type of an expression when it comes to graphing it? And so the simplest thing to do is to, for instance, consider a table where we consider different positions, that's x and y. I've chosen 4 here. And so what this means is that if you've chosen a value of x and 0, that means x is minus 1 and y equals 0. Then you take this information and you substitute it directly into this vectorial description. So that means that minus 1 becomes the y component of the vector field, and 0 becomes the y component. So this becomes a vector field 0, minus 1 at location minus 1, 0. So minus 1, 0 is here. And you'll notice that the vector field happens to be pointing downwards, that is, in the direction of minus y. In this case, minus 1 and 0. Now we can do that for a number of points, but I've chosen 4 points in particular to get some sense of what this field would look like. So for instance, 0, 1. At 0, 1, basically, we're looking at a position which would be up here. But at this point, if we substitute 0 and 1 into this expression, we end up with a vector which is minus 1, 0, which means it's pointing to our left. We can go through the other remaining 2, and we end up basically with these remaining 2 vectors, 1 here and 1 here. Now, if you look at this, you'll notice that the vector field points to the left, here points down here, points to the right here, points up here. So this appears to be a vector field that forms a closed loop. In other words, it has a circulation type pattern. And as you move outwards, then clearly the magnitude of this vector field gets larger, but it still is in the form of a circle. Right? So you can see this one scales, gets larger and larger as you move further and further outwards. The other thing we'll find is that we're using the word a radial field quite often. And so what does that mean? All right, so definition of radial field, we've got the 2D version and the 3D version. This is the 2D version, this is the 3D version. Here P is a real number and K is a constant. And so anything of this form we call a radial field. So R base that you see here is this vector xy. This is just the magnitude of this vector field to some power P. P can be positive or negative. This is just some arbitrary constant. Here what we've done, we've essentially brought this out to essentially create a unit vector. So this is the R vector. If we take that and divide by the magnitude, that means we have to modify the expression. This just becomes P minus 1. So this is the magnitude. This is the direction. It's a unit vector. In other words, its magnitude remains as 1. This is just another way of basically expressing this, but in terms of a magnitude and the actual unit vector. The only difference between the 2D case and the 3D case is that the vector field has a third component, which is z. The magnitude in this case would basically be just the square root of x squared plus y squared plus z squared, has the same form. And again, we can convert this into a unit vector, and again, has a similar form, a similar structure. So we'll be using this quite often. This type of vector, though, is clearly a circulation field. Notice this is x and y. This typically means we're dealing with a radial field. All right, so next thing is to look at specifics of geometry, because we're going to be looking at tangent vectors and normal vectors and different types of contours. So what I've shown here, for instance, is in 2D, called an open contour, just basically a curved line between 2 different points. This is basically the same idea, but in 3D. It's a curved line in 3D. And this represents the normal to a 2D between 2 points. So capital T will be considered as a unit tangent vector, and ds will be the magnitude of a differential arc length at any given point on this curved line. In this case, essentially, it's same as the 2D case. The only difference now that the unit tangent vector has a z component, whereas here it only had xy component. In the case of the normal to a contour, in this case, basically, the normal could be pointing to the left, or could be pointing upwards or pointing downwards. So this is a normal to this contour, ds again being a differential arc length. So definition shown here. So just want to make a comment. Note 1, the unit tangent vector t and the unit normal vector n subscript s can have two possible orientations. Okay, so for instance, you can talk about a tangent vector moving from left to right or from right to left, and the normal vector could be pointing either upwards or downwards. Usually the problem will specify which orientation to consider, or the orientation is decided by some specific convention, which is usually tied to basically the notion of the use of right-handed coordinate systems. All right, so let's then look at different type of contour, one in which is closed. So I've shown different combinations here. So if you notice this contour, which is a closed contour, this is discontinuous along the contour. In other words, if we were to track this line we're looking at is not a smooth continuous line. It clearly shows a discrete change. So it may be continuous, but you would not be able to consider going in this direction as being differentiable. So in this case, we would have to describe each one of these four segments by its own unit tangent vector and differential arc length. All right, so that's basically what we're seeing here. Here's another closed contour, but in this case, it's one continuous smooth curve, so we can describe this by one differential tangent vector, again, t being the unit vector, and ds being the magnitude of this differential arc. This is just differential arc length. If we look at 3D, then we could have we could have a contour of this form in 3D, which would look like this. For example, doesn't have to be. Or you could have a closed contour which is continuous along the contour in 3D. So this would be the 3D analog of the 2D case. So this, and this, and this, and this. Again, note one, the unit tangent vector t and normal vector ns can have two possible orientations, and as I stated in the previous slide, usually the problem will specify which orientation to consider, or the orientation is decided by convention. Again, just to reiterate that a normal vector ns in 3D is not considered, since there are an infinite number of choices to consider. So for example, if we were to choose a normal vector to this contour here, then basically there are all possible orientations, one going upwards, one going down, one to the side, an infinite number of possibilities. And of course, math doesn't like that type of scenario, and so it has no physical meaning. We can say, a normal exists, but unfortunately, there are just too many choices to be made. All right, so next is, what about when we're dealing with normal vectors? So normal vectors in 2D, again, here we're looking at a vector pointing outward from this segment. And since this is not a smooth contour, means that we have to define four different normal vectors. This, of course, these are unit vectors and the differential arc length magnitude. This would be a closed contour, discontinuous along the contour, discontinuous in terms of differentiability. This is a smooth contour, so this could be easily described by one normalized vector. If we move to 3D, then we can still talk about normal vectors, but we'd be talking about vectors normal to surfaces. And so, for example, if we have a closed surface, well, we can have an open surface as well, but if we'd have a closed surface and you want to describe the normal vector to the closed surface, then if it's a cube, these surfaces would all be considered smooth in these regions, but as a whole, this would not be a smooth surface. And therefore, for a cube, there are 6 surfaces, and therefore you'll require 3 different normal vectors, basically one for each one of these surfaces. Again, these are unit vectors. So this would be the unit vector normal to this surface, ds being the magnitude, the differential surface area of a surface element on this surface. We can also move to a smooth surface, such as a sphere, in which case we only need one differential vector to describe the normal to that surface. Again, this unit vector, and this is the magnitude of the differential surface area at any given point on the surface. So just a couple of summaries here. Then n subscript s, where s is lowercase, is a unit vector normal to a contour. And subscript s uppercase is a unit vector normal to a surface in 3D. ds is a differential arc length in 2D. ds, s being capitalized, is a differential surface area in 3D. And again, as we mentioned before, the unit normal vectors ns and ns can have 2 possible orientations. Again, usually the problem will specify which orientation to consider, or the orientation is decided by convention. So that more or less basically describes the sort of problems that we'll be looking at in the subsequent weeks. Okay, so next thing to do is to look at, well, can we basically look at various possible combinations of taking dot products between two different vectors, where one of the vectors is just that, a vector, and the other one is a differential vector. So if you look in the row here, you'll see TDS, NDS, TDS, NDS, N capital SDS, N capital SDS. So these are your differential vectors that you see here. Okay, so this is a differential length. Tangent to vectors is a differential length normal to the contour. This is a differential surface area. Differential length perpendicular to the contour. This is a differential surface area perpendicular to the surface. Same here. The only difference here is this is an open contour and this is a closed contour. This is an open contour. This is a closed contour. These would be 2D, 2D. And this is a surface in 3D. This is an open surface, whereas this would be a closed surface. Now we're going to give labels to each one of these things. If you see something like this, where you're going to integrate from an A and a B, we'll describe what all this is shortly. We're going to call this whole entity, which is a scalar, partial circulation. The textbook doesn't say it, and it has no physical meaning, but units-wise, it's still a circulation. Flux, on the other hand, doesn't matter. Flux basically can be over a small patch or over a closed surface, right? So we can either basically, in this case, a closed contour. So this would be basically an open contour, just a small segment, and this basically would be over a closed contour. Right, so we're going to define anything involving a normal to something, dot product with a field, as flux. This whole scalar is called flux. Now this will be the definition for circulation, where you go once around a loop. In fact, when you talk about a circulation, intuitively, you talk about going around the loop. So this is the actual definition for circulation. So this is flux on a closed contour. This is flux on an open surface. And this is flux on a closed surface. So like I said, anytime you see a dot product with a normal to something, it's by definition going to be called a flux. So this is 2D or 3D, 2D, 2D or 3D, 2D, only relevant for 3D. So here are now the different definitions. ds bold is the differential arc length. It's a unit vector which is tangent to the contour times the magnitude of the arc length. Or it can also be written this way. This would be the differential surface area, a vector, which would be the unit vector that's normal to the surface times the magnitude of that differential surface area element. Also, this vector can be written like this. So this is basically ns would be the vector normal to the contour at a given position on the contour. Magnitude of differential arc length vector is this thing called ds. So now let's look at how these things typically might be used. So let's look at what we call geometrical outcomes and physical outcomes. Geometrical, where we're measuring things like area, length, and so on. So let's say we take this expression up here. We're going to be interested in more or less these four. So if I take f and let it be equal to t, okay? I'm just doing it for sake of argument. Right? Then if I take this expression, substitute for f, I have the dot product between two unit vectors, so I'm just left with integrating from AB ds. What is that? That's just the length of a curved line between two points. If it's a closed contour, then this would basically be the total length or circumference, right, of the object or closed contour in question. Now the units of this, of course, would be meters. If you integrate ds, will be meters. You can also do it with the normal component. If I took f dot ns and let f be ns, the dot product between unit vectors would be 1. And you'd still end up more or less with exactly the same expression. Physically, what does it mean? It doesn't mean anything, but mathematically, it's perfectly okay to do so. Tangent vector makes more sense because you're moving in the same direction in which you're trying to measure length. In the case of the surface area, we can go through the same idea. So for instance here, if we let f be the normal to the surface, the unit vector, then the dot product between these normal vectors is 1, and you're just left with integrating over a surface. This would be over an open surface and be over a closed surface. And units, of course, would be meters squared. So this would be for the 3D case. The circulation or partial circulation, either 2D or 3D. But when we're dealing with 2D and we're looking at flux, the flux formulation, or basically integrating, letting F be NS, then this can only apply in the 2D case. All right, let's look at it in terms of physical outputs. Let's say F represents something in particular. All right, so I've basically written out that F dot ds, this is a form of partial circulation, no physical meaning. This is circulation. And so if this is circulation, well, what are the units of F going to be? ds is units of length, right? So if the net result of this integration is circulation, then F will have to have units of circulation circulation per meter. And this would apply in the 2D and the 3D case. On the other hand, flux, it's a little bit different. So for instance here, if we define this as being flux, as we said earlier, right, and this is length, then in 2D, flux would have units of flux per meter, flux density. So that's units of F, the flux density, be in terms of flux per meter. If you're dealing with a surface though, all right, so in this case, basically, this has units of meters squared, but this still has units of flux. That means that the flux density F will have units of flux per meter squared. Now, the moment you hear the word flux or circulation anywhere, it immediately refers to a vector property. If I just said density, like charge density, that's a scalar. But if I said charge flux density, whatever that would mean, that is a vector. Okay, so words are important here. All right, so the next thing to look at is a physical interpretation of line integral quantities. And in this case, the vector field F is replaced by some scalar coefficient times the unit tangent vector T. And this S is just symbolic. We'll basically explain what this actually looks like in real form shortly. So if we then take this partial circulation integral, replace F by lambda st, then the dot product between two unit tangent vectors that are parallel to each other will just give you 1, and so we're just this lambda sds. If we're dealing with a closed contour of the dot product between these two vectors, this being a circulation integral, then we end up basically with this expression, which would be around a closed contour. And this represents nothing more than, for instance, whatever this lambda over s is, some physical quantity, such as a mass density at a given point on a curved line segment. Its units would be, in case of mass, kilograms per meter, and if you integrate over the length of the curved line, that gives you the total mass on the curved line. Could have also used charge instead of kilograms if we're interested in the properties of charge on a curved line. So this would be for the case of 2D or 3D if we're dealing with the unit tangent vector. However, when we look at the normal vector, normal to a tangent vector, then this only has meaning in a 2D geometry. And so in this case, all we're doing is representing F now in terms of this scalar coefficient, similar to the one above, but times the unit normal vector. And so F gets replaced by lambda s n of s, but the dot product between two unit vectors that are parallel to each other equals 1, and we end up with more or less exactly the same expressions. Now, from a physical perspective, thinking in terms of a normal and relating this somehow to this problem at hand has no specific meaning. This is purely a mathematical exercise. It just shows us that if we take a vector of this form, then we end up basically with something that describes the physical properties of a curved line. Lastly, if we go to 3D and we're using a normal, then we're dealing with a normal to a surface. So in this case, we're representing the vector field F by some scalar coefficient times the normal, unit normal vector to a surface. Replacing F in the calculation for flux would give you basically dot product between two unit vectors which are parallel to each other. And so we end up again with a scalar coefficient ds. This sigma s now would be considered as a mass density, which would have units of kilograms per meter squared. This, of course, would have units of meters squared, so this would be essentially computing the total mass over a curved surface. The only difference between this expression here And this expression is, in this case, we're doing an integration over a closed surface, whereas here it was over an open surface. Now, in actual fact, what does lambda of S actually, what does it represent? It basically means that when we parameterize a contour in 2D, we need a parameterization variable, which means we're picking off what the charge density is at every given point on the line, defined by the variable u in this case. So there's x and y component. Similarly, if we deal with a 3D contour, then we would have an x, y, and z component, but the contour is parameterized by the variable u. If we're dealing with basically a charge density in 2 dimensions, and any type of surface area is parameterized in terms of 2 variables. These new variables are u and v, and so there'll be an x component and a y component. And if we move into 3D, the only difference is that we now introduce also a z component, as this will become an oriented surface. All right, just to sort of a general reminder then, that the unit tangent vector t has more physical meaning when computing a geometrical physical property of a curve, such as the length or charge mass, respectively. So our definition, in terms of how we've laid things out here, make it possible to use a normal unit vector ns instead of t, but don't read anything physical into it.
Okay, so one other thing I'd like to mention is averages. Now that we're dealing with curved surfaces, curved lines, we're not restricting ourselves to planes anymore. Can we still use averages? The answer, of course, is yes. And so in this case, if I have a curved line, and I want to, for instance, I want to find out what is the average mass along the curved line, then this F would be the mass density, which would have been something like lambda. And I integrate that over the length of the curve and divide it by the length of the curve. That's the average of this entity that you see here. So if this, like I said, this was a mass density, this would tell you what the average mass density is. Similarly, if you're dealing with a curved surface, then basically what you'd be looking at is something here which involves, say, kilograms per meter squared, and you're basically computing the total mass on the surface and dividing by the area of the surface. So this gives you basically the average mass density. You can also do with the volume as well. In this case, basically, this would be a volume density, and this would be an average volume density. Now, there are other things you can try. For instance, here, where it's a weighted average. This would represent the mass-weighted average position for a curved surface in 2D or 3D and volume, respectively. These are color-coded. So, friends, you have a curved line, and you're trying to figure out what is the balance point. If I basically took the curved line and put my finger at a certain point along it, at what point would it be balanced? And so that x average point would be more or less telling you where the balance point is. This is assuming, of course, that the gravitational field is constant, which generally is the case when we're dealing with terrestrial problems. The problem would have to be reformulated if the force varies as a function of position, or force field as a function of position. You can also do it for something which is a curved surface. So this would be the sort of the balance point for the x component. You can also do it for volume. This would be the x balance point in the case of a volume. Now, you can also basically do the same computation for the y and z component if necessary. If it's a two-dimensional object, then you'd also have an expression for y here. If it's a three-dimensional object, you would have expression for y and z as well. So there'll be an x average, a y average, and a z average. So these are things basically that we're not going to be looking at. The mathematics is straightforward. However, a more detailed discussion of this topic is given in chapter 16.6 of the textbook, which we will not cover, nor are you responsible for it. Well, that concludes lecture 17A. Thank you for listening.